Hi everyone, thanks for joining me. In this next section, I'd like to talk to you about moving from data and going beyond data to information theory. Now, we know that deep learning AI systems have provided extraordinary results in recent times, and what we're looking at though is how do we build AI systems that are capable of handling particularly difficult problems in terms of social context, awareness, and expanding upon those areas. So we know that there are some significant flaws with the current ways of building models, and it seems that there may be a need for introducing and building new models. It may be possible to complement the existing models, and yet at the same time we are aware that there needs to be something rather different than what's done at the moment. And our starting point in all of this is to reconsider what's meant by data. Are we really interested in data or in something else? So let's consider this now. Let's go back to the question of how do we know unusual or unexpected behaviours? So if you can think about this example here, then as you can see, there are sometimes unusual behaviours where we can easily identify them. For example, we can set some particular boundaries, and if a data point exceeds that boundary, then we can do something about it. So that's not quite really what we're talking about. On the other hand, if we move to, for example, considering speech, if we look at this speech signal here, then we might consider a similar approach. We could consider that a particular word is said, and then this would lead to a particular response, and this is a very well-defined approach. But how could we handle what actually happens in human behaviour and perhaps understanding the true meaning of what someone's saying? We know that hesitancy might indicate something deeper, and so although a person says yes, if there is a pause occurring, then we understand that this might actually change the meaning within the speech itself. And so in this particular situation here, we can take the speech signals and then extract out the pause information across the speech. And perhaps this might lead to something altogether different than the direct speech signal. Is there a general approach which could be applied to widely varying agent behaviours, for example, biological systems, vessels, vehicles, swarms, or really almost any dynamic system? Ideally, such a model could be used to form a model of the behaviour of systems, whether it's in speech or written form or digital signals, or even perhaps vehicle movements, wherever they may be and whatever their size. So let's take a step back and consider perhaps the most basic aspect of these models. How can we tell the difference between objects? So this is the fundamental basis for modelling. That is, being able to measure the distance or the difference between points in the model space. So let's talk about measuring the data. Supposing we have two vectors, A and B, then the distance between those two vectors can be found by the usual well-known Pythagorean formula. And here we have the distance d given by a simple equation in a Cartesian coordinate system. And this is known as the Euclidean distance, and in fact is the general basis for most or many value-based machine learning systems. But how can we measure this distance if there are non-numeric entities? In other words, supposing you're dealing with items such as food or animals or something entirely different, how is it possible to measure the difference between behaviours, for example, in, let's say, conversations or in swarms? How is it possible to do that when there's clearly no direct Euclidean distance that we can measure? There is no ready Cartesian coordinate system where we can simply measure the distance between groups of objects. How can we measure something in these rather unusual cases? So, in 1948, Claude Shannon was working on the problem of how many messages could be transmitted via a telegraph line, or what we call the channel capacity. To solve this problem, he realised that the issue here was that he had to define what's actually meant by a message in very fundamental terms. In other words, he was thinking about the capacity in terms of messages, not data. So this requires a slightly different way of thinking than many of us are accustomed to. So for example, we can think readily in terms of memory bandwidth or transmission speed, for example 1 gigabit per second or something. But here we're talking about something else. For example, we can say that there is no message if the message is already known. And we might begin to think about this in terms of information, and the information is something that we didn't already know. So this simple idea has opened up the doors to a remarkable field where we're concerned with processing something even when we don't know what it is. And so we can begin to consider the information transmitted from A to B. Note that we haven't actually defined what that information is or the way in which it's transmitted. And this actually is a starting point for what is termed information theory. It's actually an amazing thing that although this was developed about 70 years ago, it really is starting to come out as being something of considerable interest at the moment, because it really speaks to the fundamental nature of what's contained in the data, and that is the meaning or the information, the message if you like. So how do we move from measuring distances in data to measuring something that we can call information, the measurement between entities if you like, that tells us what we want to know? Now what we're interested in is not the data but the information. So how can we measure, or rather how can we define actually what we mean by information more precisely in this context? So let's consider the following sequences. On the first line we see that there's really nothing new. After the first few letters there's really nothing new that you're learning. It's pretty clear what's happening. And yet on the bottom line we can see that there is some sort of coded message. Now another way to describe this is that actually in the first line there's nothing interesting happening, but on the second line there's a degree of surprise. Think about it this way. If we say the same thing in a conversation, then if there's nothing new, there may be a lot of data, but there's really no information. If you want an interesting conversation, you might say, "Tell me something new." So it's not so much the data that's important, but it's actually the amount of something new that's being received. So Shannon described this idea as the degree of surprise. It's interesting to think that we can actually measure surprise or unexpectedness in a probabilistic sense. And this is perhaps his key breakthrough in understanding, recognizing, then building upon this idea. Suppose we've got a sequence of characters and then the probability of each symbol can be analyzed and calculated. This actually gives us a degree of surprise. So the probability conveys a simple measure of information. Okay, so looking in this next slide here, let's consider a more concrete example. Supposing we have an event B and another probability, an event B with a probability of 1/25, and then we have a probability of 1/10 for an event C. Then we might say that B is surprising and C is also surprising, but with different amounts of surprise. So how can we use this concept of surprise as a measure of information? What we really want to do is consider relative surprise. We want to normalize all of the surprises so that we can account for even the very rare events. For example, a change in the probability of X from 1/100th to 2/100ths is still very rare, but may actually still be quite significant. So we don't want to lose that information or that particular point. So the way to proceed in this is that we sum the log normalized probabilities, and this actually gives us a definition of what is termed Shannon entropy. It is a way of capturing all of the surprises across a whole data set consisting of various symbolic events and then presenting that in a simple way. So the way that we calculate entropy is very simple. We determine the probabilities of each event, we take the log, and then we do this weighted sum. That's really all there is to it, at least in the first instance. So note that these symbolic events can be anything at all that we observe. Let's move on and have a look at a particular example. So, supposing a friend of ours named Joe has a diet of 4 types of fruit or vegetables. And they're a good friend of ours, so we say to them, "Hey Joe, can I measure the entropy of your diet?" And since they've recently read Shannon's 1951 paper on information theory, or because perhaps they're also more than a little bit curious, they say, "Sure." So you begin to measure Joe's diet and you calculate the probabilities, that is, the number of times that he eats certain types of fruit or vegetables, and you come up with a figure of 1.83 for his entropy over that time. Great. But supposing that you decide, what if I could calculate this entropy over short periods? Would that help me? Well, you do that and things go along nicely until one day you notice that the diet entropy for Joe has dropped. Now, perhaps your good friend Joe is unwell, so you call them to find out the problem. But they say, it's okay, the farmer's market had a special on bananas, and he explains the situation. And so you're relieved that although the diet entropy was dropped, they will live. Now, let's talk about something else. Let's talk about trust. Trust is often misdefined, for example, as variance or uncertainty. And this is evident when we see measures of trust changing rapidly. However, trust should really be defined in terms of social behaviour. Now, since entropy provides a method of modelling social behaviour, this actually provides the mechanism we need to model trust. And so, if we're going to consider changes in behaviour, this actually helps us to understand a mechanism of modelling relative trust. Now, in the next section, I'll talk to you a bit more about actually how we calculate entropy and how that's applied. Thanks very much.